Hello everyone. My name is Courtney. I'm a founder and CTO, CTO. I used to be CTO. I'm founder of a small startup called Hippie. What I'm going to talk to you about is basically what we spent the last 3 years building, and what we're just basically taking into public beta and will be open sourcing later this year. The talk is. Can I first see just a show of hands of how many people here are actually technical? Oh, excellent. Because if you weren't, then this is not the place to be. So the talk is going to start off by just talking about a bit about the problem that we're solving, what we're doing and how we're helping people. And then I'll go into some of the details about how we've built some of this. So if you guys have been around to some of the talks, you've seen GridGain, obviously, and Apache Ignite. So the platform is built on top of Ignite. So there are a number of things that we'll run through. We're a relatively small team at the moment. I think we're 7 now. And we've got a couple of them lying around somewhere. Nobody actually came. Oh yeah, I've got one. All right, so one of them actually came to the talk. The rest of them are wandering around somewhere. So Hippie is a platform that basically allows you to get from your idea or whatever it is you're looking to build, so going from idea to production in a couple of hours, if that's what it takes you to basically write a model. What the platform does is it's very model-centric, so you would write a model about what it is you're building, you would annotate it, and you say, I don't know, you're looking to get data from these places, your data looks like this, etc. So you'd build out this model of what the world looks like for you and your application, and from that, the platform then looks at the model that you provided, the relationships between all the models, and it generates an API that you can then start using at the click of a button. In a nutshell, that's the basic and core functionalities that we provide. And on top of that, we've then built out a number of other things that makes it easier to do application development. Right. So that in a nutshell is what we've built and what we're currently still working on. So there are a number of things that we've provided on top of the basic functionality that I just mentioned. One of them is serverless functions. So if you've heard of lots of graph databases, you might know that it's not very easy sometimes to work with some of them. There are times when you're looking at data, you'd like to do something either relatively simple or really hard, but there isn't a very easy way to plug into most of them. So to do that, we have support for serverless functions. There are 2 types. There's one where we actually compile code on the fly and then execute that in the same process, so you get data locality. And then there's another version that actually you can do, if you're familiar with Google's Knative on Kubernetes, you can basically, whatever you can package into a Docker container, you could use that as a serverless function as well on the platform. So off the bat, you get a ton of stuff that you click a button and you can start working against that. A lot of companies nowadays are popping up in what's being called a low-code space. And if you remember, probably about a decade ago, there's a whole thing about rapid application development. It's basically the same thing coming back again under a different name. But that's kind of the category that we fall into. So you would design your model, like I said, and at the click of a button, you can then start building against it. I'm going to talk to you about what that looks like and how we've built some of that. So I skipped ahead on most of the stuff that's on my slides, but in a nutshell, you, you end up with, from your model, you end up getting the ability to do compute. So if you're familiar with like AWS functions or Google functions, any of the serverless platforms nowadays, you get that. You get storage. Like I said, we're built on top of Ignite. By default, that's in memory as well, hence obviously the conference. You get authorization off the bat, so lots of applications have to be or have authorization built in, not just anyone can access various things. So off the bat, we have about a dozen, I think, different types of policies that you can create to define whatever organization authorization policies that you need to do. It's scalable. In general, all you need to do is just add more nodes. And I think until you get to a couple hundred, you don't need to do anything extra. After that, you probably need to use Zookeeper depending on your environment. And it's extensible. So the serverless functions that I mentioned earlier, they're not just for operating on the graph. You can use them to build custom functionality that's got nothing to do with the platform itself. So I don't know, whatever your app was doing, you could build applications that works on the platform or with the platform and extend it. It's very declarative, so we, and I'll come on to this in a second, but we use GraphQL. GraphQL is a technology that was open sourced by Facebook a couple of years ago. Basically, you can define a data model and you also get a query language along with it. And our platform is basically built around that. So the API that you would get by default is a GraphQL API. We will be adding support for REST in front of that. So most applications nowadays, you'll tend to have tooling for REST type APIs. We'll be adding support for that later on, but right now it's very GraphQL centric. It's very big. There are lots of things that you get from Apache Ignite, for those of you who don't know. At the center of Ignite is the idea of caches. And you can think of a cache as kind of like a table, but it's really not. It's basically a key value store. And the entire platform, the whole graph database is built on top of these key value caches. Ignite also has machine learning support, so that, of course, we expose through the platform. We're working on basically having an app store. One of the functionalities that you get as part of our platform is, let's say you've got teams working on different pieces of functionality in your organization. You can have one team build something completely different in their own time, release it on their own schedules, etc. And at the click of a button from the platform, you can just go, I'd like to depend on that. And you inherit the behavior from that app, no additional effort. You can then start to customize that. And obviously, you'd have to define the authorization policies that lets you control that, but you're able to do that at the click of a button as well. So from the outset, the things you get by default is basically a CRUD API with trash. So if you use like a Google Drive or another storage service, they have the ability to go delete, but it never actually goes straight to delete. It gets stored there sometime. That's basically trash, right? So you get a CRUD API plus trash by default. We have, like I said, machine learning support. So just from defining your model, you automatically get the CRUD API. So you've got storage sorted. You then get the machine learning stuff. You also get full text searching as part of this. So if you were looking to index and be able to search your data, that comes basically built in. You don't have to do anything else extra for that. Another thing that you get automatically is support for streaming. So if you've got streaming platforms, I know there are a few talks that people have done yesterday and today. If you've got like a Kafka stream, etc., or let's say, what's the AWS IoT thing that they use, can't remember the name, but you could integrate with any of those as data sources to get data in or out of your application. All those automatically, just from designing the model, pressing a button, end of story, you get those as part of the platform. The other thing that you get is automatic integration with various cloud platforms. So we're still working on building out some of the integrations that you get by default, but off the bat, you're able to annotate any of your models and then integrate with, for example, something that's running on AWS, something that's running in a private environment, or wherever else. If it's accessible over a network, then you can automatically integrate with it by annotating your data models. And I'll show you what the data model that I keep going on about looks like in a second. So that's kind of what the product and the platform is. And I'm going to talk now more about how it's built, right? So that's kind of the diagram I had at the start about that descent. This is what the platform does, and now we're going to go look at how it works. For people that don't know, we were at a conference, we were in Canada like 2 weeks ago, and when I spoke to somebody about what it does, the guy looked at me and he went, wait, you can do that? And you just see that look on his face. That was very pleasing. It's kind of like magic. For people that don't really know how it works, it is kind of like magic. But like I said, at the center of the platform is GraphQL. So you start everything with your data model. You start by designing what your application's world looks like. You then go on to annotating those models, and the GraphQL model is, if you know Java, I don't know, any other language that allows you to do classes, basically think of a class, has no methods, just a bunch of fields. GraphQL model is nothing more than that. And then you can start annotating the fields and say where the data comes from, what the data looks like, and what you want to do with it. It's very good for environments where, for example, I think Facebook said they originally did it for their mobile application, because one of the features of GraphQL is you can choose exactly which data you'd like to get back in your responses. And I'll show you what that looks like in a second. We're not going to actually practically do this. I'm just going to walk you through basically what you would do if you were to build a to-do app that had some of these features, right? So you wanted to create a to-do app. It's just task list, title, some other fields, job done. A GraphQL data model starts to look like this. Basically, you have types, like I said, if you think of a class from another language, and then you've got fields inside that. And that's pretty much it. In the language, you've got support for types, enums, interfaces. Basically, think of all the object-oriented concepts that you're familiar with. You've pretty much got most of them in GraphQL that you can use to define your models. The things on the right, so at field in GraphQL, that's called a directive. And that's how we extend and allow you to extend the platform and the features that you get by default. So you can write your own directive, or you can use the ones that we've got built in. The one that I've got and reuse in several of those is field. What that allows you to do is to index the fields in your model. So on those fields, it's basically saying, okay, I'd like this field to be indexed. The very first one, slug, that says type keyword. Keyword is good for when you've got things like IDs that shouldn't be broken up. By default, it indexes it as if it was like a search engine. So you could then search for any term that occurs in those fields. So that's what you could do if you were building a to-do app. And by default, you would then get those features, right? You don't have to do much else to then get all of these features as well. What the platform does is we would automatically inject an additional field into each of your data types, and that we basically control what goes into that, so you can't modify it. But what it does do is it gives us the ability to allow us to basically automatically get you pagination. So you don't have to work out how do I go from page 1 to page n. You've already got support for that by simply designing your model. The authorization stuff that I mentioned earlier, that also comes for free. The way that would work is you would create a policy, and your policy can apply to a type, it could apply to a specific resource, or it could apply to an arbitrary string. So like, for example, if you wanted to protect a URL, you could do that as well. And you can use your policies to protect anything that you design. So from that simple model, what would you think the platform looks at? Off the bat, the thing that it focuses on is relations. So I'll go back a second, but if you look on the models where you've got item and then attachments and comments, the relationship between those objects is what's important as far as the platform is concerned. It will use that to define the relationships in the graph that it will then work with underneath, right? So everything that the platform does and the way it operates, it basically just looks at the relationships between the models that you've created. So, for most people, they're not really graph experts, so I'll just give a brief intro to what graphs are. I don't mean charts. I mean a graph where you've got vertices and edges. And in any graph, I really need to change that from having black arrows to white or something. But A graph is basically made up of vertices and edges. Your vertices will be basically if you've created an object, and then your edges will then, if you've got two objects and you'd like to have some relationship between them, you create an edge between the two. Most of this happens by default. You don't have to do anything. It's only if you would like to start customizing the behavior or changing it that you would then actually need to know any of this. But this is basically how the platform is built. Now, one of the things that causes real problems when you start to scale is what you're doing with the data. And for most applications, the data will be mutable, right? And mutability in a very large system can cause a lot of problems. So one of the things that we do is actually we try not to mutate stuff. And for a lot of people, as soon as you go, everything's immutable, they go, oh, but that means it's so slow, or there's so much wasted space. That doesn't have to be true, right? In general, there's the whole thing about the cap theorem. If you're building a distributed system where you would need kind of consistency, availability, and partition tolerance, you can only really get two of the three of them. That's true, right? And we're not breaking the laws of physics or anything, but you can design the system such that you basically sidestep some of the problems that are created by those things, right? And that's effectively what we do. This little relationship at the bottom, just bear in mind for later on. But basically, we treat the data that goes into the platform as sets, kind of. And one of the things that we do is in the cluster, we'll start partitioning the data. And a lot of that is based on, I guess, like high school maths about sets, really, I guess, primitive stuff. The other part that makes this interesting in what we're doing is category theory. Hands up anyone who's heard of, knows of, or has done anything category theory related. One person, excellent. So category theory basically allows you to think about, that's the best way to describe this. In category theory, you've got objects, right? And not objects as in an object-oriented language. Basically, everything is kind of an object, right? So if you had an item, that would be one object. If you had relationships between several objects, then you would basically start getting what in category theory you basically call arrows. The only reason that's called arrows is just because of the relationships. In general, what that allows you to do is it allows you to start looking at your data and everything that you're working with from a computing perspective in a more mathematical way. And there are certain properties that you get with category theory, and we take advantage of a lot of those. So, for example, one of them is how you do traversals. So just on the right, that diagram, where you've got A, B, and C, right? If you're looking to traverse a graph, typically you might need to go A, B, and then C, right? But imagine if you could effectively just go, well, I know everything in between A exists, and I just want to get to C. Category theory effectively allows us to operate as if we've been to B and completely avoid the traversal in the first place. And that's one of the things that we do to achieve some of the performance that we get in the platform. So when that all comes together, you effectively end up with another distributed system, right? And for us, one of the things that I've been working on, so I'm also a part-time PhD student, and one of the things that I've created as part of this is what I've been calling wormhole traversals. So the thing I just explained about basically being able to skip stuff in between, that's basically what a wormhole traversal is. Because of the properties that we, I guess, adhere to around category theory, we in the platform, when we're doing graph traversals, we can effectively avoid traversing several vertices between 2 points. So if we're looking to find, all the data that's connected from A to G in this case, we can effectively skip B and C. That's effectively what wormhole traversal is, or what it does when you're operating with the platform. And again, most of this you never actually have to work with. You can if you choose to, but I can't imagine a use case where you'd actually want to go that low level. But it is accessible, and you can change how most of it works. That's basically wormhole traversals. Now, one other thing that we end up having to do is basically an optimization. So if you've got graphs like, imagine Twitter, right? And you get somebody that's very popular on Twitter, take the Justin Biebers or the Barack Obamas of the world, and their Twitter accounts, they have tens of millions or even hundreds of millions of people that are following them. Basically, that means you're creating hundreds of millions of edges into this one vertex in your graph, right? That's not good for a distributed system if you want to be able to operate on that very quickly. So the next technique that I've created as part of my research is what I'm calling cascading vertices. Basically, it allows you to partition the data for a single vertex and still be able to operate on it in the database as if it was all like one unit, right? So the partitioning is relatively simple. Imagine you have 3 nodes, right? And you've decided that for the largest vertex the largest vertex that you'll have in your graph, you've decided that 3 servers is enough to store them on. When an operation occurs to add an edge to that, first thing that might happen is it will go to server 1. But then let's imagine that at the same time, I did that in the wrong order, sorry. The first thing that happens is your data will get replicated over to 2 or 3 nodes in the group of servers, right? Then as your vertex gets bigger, so as basically more edges are added to it, at some point the partitioning algorithm will start to cascade that data over to other servers. From you operating on the graph, it's completely transparent. How it chooses when to do the cascading is configurable, but by default, again, you don't have to do anything. It will try and work out some sensible number for you, depending on the size of your graph. And in effect, this continues. So every time some more data gets added, it will basically just start cascading and cascading and cascading. You operating on the graph, you never see any of this, and you work with that vertex as if all the data is in one place, as if it's just one thing, right? And the whole thing repeats. So you get to the end, and you've decided that I just want to split this across 3 servers if it gets too big. When the threshold that it determines is reached and you've gotten to 3 servers, it will basically wrap around and repeat the whole process over again. Another technique that we've had to use, so this one's a published work by someone else, an FM index. So basically, it allows us to determine, is this thing connected to this other thing? And it allows us to do that very quickly. In fact, most of it is just bit operations. But effectively, it's in-memory data structure. It's very succinct, so it gets very close to the theoretical minimum that you can use to store the actual data. And for every vertex in the graph, it allows you to determine whether there's a relationship from that vertex to the other one. But more interestingly, it allows you to traverse all of them without having to go to the actual database. You can basically say, okay, for this vertex, tell me all the other edges that it's connected to. And you can do that by just simply traversing the data structure, which makes it very quick, because you don't need to do any I/O lookups. The only thing you're basically working with is RAM. Right. So those are kind of the big components that we've brought together to build out the underlying platform for this. And like I mentioned earlier, it scales. We've done a recent project that had over 7 billion edges in it, and most of the requests, you wouldn't have thought that it had billions of connections in it. There was like sub-milliseconds for some of them, depending on what you were trying to do. Obviously, the latency on your queries is dependent on what you're trying to work out, but in general, you're looking at like a couple of milliseconds to do an operation across the board. So, I'll touch on how we hook into Apache Ignite to be able to do all of this. Ignite, like I mentioned, is a memory-centric platform that effectively has these things called caches. And a cache is kind of like a table, but the only thing you get is a key, so you've got an ID for something, and value, right? So it's a key value store. It also has built-in support for Apache Lucene, which is a big project that basically allows you to do indexing. So the annotations that I showed earlier where you were saying, I want this to be a keyword, etc., that's basically telling the platform how it should basically generate the indexes that it will do in Lucene for your data. Right. When you create models in the platform, every data type that you get effectively ends up going to its own Ignite cache. And what that generally means is that for every model, you'll end up having as many Ignite caches. So even though you're free to create hundreds or even thousands of those, the more of them you have, the more memory it will require for you to be able to support all of those. That's probably the only caveat I need to point out. But basically, it automatically maps all of these for you. And Ignite has support for persistence, so you can configure it to start storing data on disk for you. But actually, because of what we're doing, we abuse it a lot. We abuse Ignite a lot. And we had some issues with the built-in persistence that it had, so we had to basically replace that. And it's pluggable. Ignite is very pluggable. It actually has an API that lets you swap out all the pieces, which is what we've done to be able to do the persistence ourselves. And what we did, we ended up choosing RocksDB, which again is another Facebook project, which was forked from the Google Level DB project. But one of the things that we really needed was multi-tenant support. Our platform, right now it's SaaS-based. We will have on-prem support, but right now it's SaaS-based, which means that we need to be able to isolate each tenant's data, right? And if you have two customers that's got the same model name, then they'll map to the same cache. But actually, they don't get stored in the same place, not on disk anyway, right? In RocksDB, you have the idea of a column family. So every tenant will effectively get their own column family in RocksDB, basically creating that isolation for customer data. The other thing that's worth mentioning is that relationships, as they're created, it's all automatic. You don't have to actually create any relationships yourself, although you can. The relationships are created and stored in Lucene as well. So when we do searches, you can basically start looking for anything. So you can ask a query like, tell me all the things that references this thing. Right? So you don't have to start from the origin. You can pick a destination and then find all the things that are pointing to it as well. So it allows you to go both directions in the graph when you're traversing. And one of the reasons we're able to achieve that is because we're doing some of the references in Lucene as well. So it makes basically the entire data set, references and the original data, searchable. The FM indexes, they can get very large. So we start, on startup, it will be partially populated, and then basically it will gradually have more data put into it. That does mean that if you ask the platform, hey, is there a relationship between these two things, or find me all the things that this is connected to, if the data is not already in the FM index, then we have to go and find that on disk. But it's just because of the memory cost. Again, that's something that's configurable because you can choose how much memory you'd like it to use, like basically a maximum on that. So what does this look like once you've actually got an API? The data model that I showed earlier, the first thing that you would get is the CRUD API that I mentioned. And effectively, for every model that you create, you end up with those functions that you can then use to operate on that model. Right? So off the bat, you're able to start searching for stuff. So there's a find method. Then you get the standard create, update, delete, and trash, like I mentioned. The thing that's highlighted in red, ArcQL, this is basically our DSL for working with the graph data. I'll come on to what that looks like in a second, but basically it allows you to treat it almost SQL-like, and I'll show you what that looks like. So it's a very simple language, and it's designed the way it is to be reflective kind of of SQL because that's what a lot of people are familiar with. But a lot of the queries that you're able to do is basically based on how you index your data. And that's why I said the model is very important, because you decide, if you'd like to be able to search for something, you have to tell the platform that you want to be able to search for it and how you'd like to be able to search for it. What RQL gives you is looks like about a dozen different types of things that you can do in the query language. So you've got term queries. I mentioned earlier that when you're indexing, if you do type keyword, it says basically that you shouldn't break this string up. I want to be able to search for it exactly as I pass it in. That's what a term query would give you. A phrase keyword is basically, imagine going to Google or another search engine, you just type something in and it will find wherever those terms occur in your data. Prefix, as the name suggests, where something starts with some string. Wildcard, so you just do star, or you can do a question mark if you just basically, if you have most of a word, for example, and you know that only one character will be different, you can you can pass in the whole word and stick a question mark in where that one character is going to be different, basically do a wildcard on characters. You've also got fuzzy matching. That again is a Lucene functionality. But that allows you to find basically words that are kind of similar. So if you can rotate or shift a few characters here and there and get the same thing, then they'll come back as being fuzzy. And you've got built-in range support. So you can find, like if you're doing dates is a good example. I want to find everything between January X and, I don't know, February another time. You can do a range query to be able to find that data. Other things that are very SQL-like is exists. So you can say, get me data where this field exists or where this field doesn't exist. And inner joins are, they are implicit. What you can do is you can effectively traverse the relationship structure of your models. So if you have a type that has a field A, and A is of some type that has a field B, and B is of a type that has some field C, when you're searching, if you'd like to find some type that has the A field, you can basically do find me where A.B.C matches some filter. So you can basically do inner joins implicitly. You can also do left joins. Those are explicit, so you have to literally type left join and then you pass some filter to it. And those will work as you'd expect from SQL. And then the graph-specific type of operators that you've got are refs, link, and onlink. And a refs query basically allows you to, like I said earlier, you can say, find me all the things that are pointing to this thing or all the things that this thing points to. That's what a ref query would allow you to do. Link and onlink, if you would like, so by default, the platform will look at your data model, look at the relationships, and if you pass in, if you do a create item, for example, and then in the data that you pass in for an item, you've got the comments field with data populated, the platform would automatically create the relationships between those for you. But if you already got a comment and you just like to say, okay, just link this comment to this item, then you can use the link query to be able to do that. And you can do the opposite with onlink, basically removing a reference between two types, basically removing the edges. And then finally, you've got subscribe. So subscribe has two forms. The first one is where you've got the ID of the thing you would like to subscribe to, and you would like to get basically any mutation that happens on that particular object. You'd like to be notified of any changes to it. You can subscribe to a specific ID. That happens in real time. The other thing that you can do is subscribe to a query, and that's near real time, so we'll limit how often that gets executed. When you subscribe to an ID, Ignite has built-in functionality that basically supports that, so we just piggyback off of that. But for the queries, we have to actually execute them every now and again. So it's not configurable how often that happens. Right now, it's every 10 seconds. So that's how long, if you're subscribing to queries, you'd have to wait to get updates that match your query. But effectively, off the bat, all of that you get by default. So how does this look once, like as an architecture, and how does it all come together? at the outset, the very first thing that we have to work with is the GraphQL API that we generate for you. So at the front of everything, we have the GraphQL engine. It will do the parsing. It will basically start looking at what you've asked for and trying to work out what to do with the query and find the things that you've asked for. That gets transformed into query tree algebra, which is basically just some data structures with a couple of functions over them. And from your query tree algebra, that effectively becomes the thing that's executed. So once we've parsed the GraphQL, we kind of then just ignore it until when we got the response back and we need to send it back. The data or the query first goes through the graph traversal engine. If you're doing queries, then that will start looking at the relationships again based on the model that you created originally. So if you ask for a query that goes from A to B to C, it will basically look at your model to work out what it needs to do and do the traversal. The A.B.C inner join thing that I mentioned earlier, the thing that actually works out what to do with that type of query is the query engine. Because like I said, each of your models ends up in different caches. So we have a query engine that basically maps your A.B.C to go off to the index with C to find your data, then link and do all of the relationships back up the chain until it's actually gotten back to what you originally asked for. That works the same, because one of the things I didn't show on the RQL slide is that you can actually do ands and or just like you would in SQL, and then you can start grouping them as well. So you can have any number of arbitrary nesting for your groups. And then the next big thing, I guess, is the policy engine. And that's the thing that decides whether you can actually see the data that matches the query that you've asked for. The first thing is it needs to be yours, right? So it needs to belong to the tenant that's asking for the data. By default, the owner is the only person that can see data that's been created. But then, like I said, you can create policies that, for example, you can do a group-based policy, or you can do an organization-based policy. And if you were, for example, working with mobile devices, you can do client-based policies, just like you would in, for example, OAuth. So you could say that the Android client is only allowed to see this data, right? You could do the same thing for Teams. So I think there's about a dozen different types of policies that you can create depending on whatever your application needed. And then serverless functions is when you do a query, we load up your model. If you've got scripts, so basically Java or JavaScript that you've submitted, we will compile the Java code on the fly and we cache those. And at any point, you can annotate. I didn't show it on the model earlier because I needed to keep that relatively simple, but you can annotate any of your fields and you can basically execute any Java code that you want at about a dozen different points that you can hook into while you're traversing your data. And that's for the built-in serverless functions. If you would like to work with existing apps, so you can basically package pretty much anything into a Docker container, and we'd also execute those in line. The obvious downside to that is we're not going to be running the Docker process in process as we do with the other serverless functions, so there will be a difference in latency depending on the type of serverless function that you're doing. So you'd have to be, I guess, wary of what you're doing with those. And then lastly, I mentioned earlier that we swapped out Ignite's persistence store for RocksDB. Now, when we've worked out whether you can access the data and what data you're trying to access, we then start going to Ignite to work out and get that actually back from the store. By default, Ignite will then cache stuff as it comes back. So we load the in-memory grid on demand as the data is requested. So we use, Ignite has basically a functionality called an affinity function, and that just allows you to say that you would like data relating to some, we have a custom function that allows us to partition the data. We do it currently by tenant, but you can write your own affinity function to do placement of the data for something that's more optimal for your use case. And then you have what's called affinity runs. So Ignite allows you to effectively, after you've partitioned your data, it allows you to decide where in the cluster you would like to be able to actually execute your code. So imagine let's say EU regulations, you're not allowed to store data outside the EU in some cases. You could basically do an affinity function that said data from this customer can only be stored and should ever only exist or be operated on in the EU or on EU servers. So you could use the affinity functions to be able to map and partition data in that way. And then lastly, Ignite's a key value store. I mentioned earlier that we abuse it a lot because we've effectively built a graph database on top of a key value store, right? And those two don't always mesh. Even though Ignite is great because it gives you functionality like, for example, transactions. So by default, your operations are transactional. So if something fails, then the whole thing gets rolled back, which isn't something that we'd want to build ourselves. So we're taking advantage of all of those things that Ignite allows us to do, but the two doesn't always mesh. So we've had to jump through a lot of hoops to be able to actually get most of this stuff working. In general, though, it's very performant, and the more we get cached in memory, the faster it gets. So actually, you might think that the more data you get into it, it'll start slowing down, but that's not the case. It's the exact opposite. The more we get pulled into the system, it actually gets faster, because we actually start doing more optimizations the bigger your caches get. That's the end. We've been building this for about 3 years. We went into private beta last year, and we're going public beta this month. Basically, anybody will be able to sign up and start playing around with it and use it for themselves. And later this year, we're planning to open source it, the entire platform as well. Thank you.